Hello, in this second module, we will address the governance of the system, our brain and the executive functions. The governance of our system, which enables us to think, decide, act, and achieve goals, resides in our nervous system. A simple initial definition of executive functions is that they are a set of cognitive skills necessary to control and regulate our own behavior. They are responsible for establishing, maintaining, monitoring, correcting, and ensuring the execution of an action plan toward a specific goal. In the context of a golf competition, where the goal is to win or achieve the best possible result, executive functions are responsible for enabling us to establish the game plan, supervise whether what we had planned for each hole and each situation is being executed, maintain that plan, and if it is not being followed, correct the action we are taking. We will see that executive functions also allow us to adapt our plan to situations that require a change, such as significant errors that force us to take a more aggressive approach. However, before delving into this and to better understand it, let's briefly explore some general notes on the organization of the nervous system. The complexity of the nervous system's organization involves an extensive neural network. From an anatomical perspective, these networks can be divided into two main parts: the central nervous system, CNS, and the peripheral nervous system, PNS. The nervous system performs a complex array of functions, ranging from environmental perception to action execution. Its three main functions are key to our operation: sensory function. This connects us to the world around us, acting as an antenna that detects both external and internal stimuli. This ability allows us to perceive the dampness of the grass or recognize the undulations of a green. Integrative function. This processes all the sensory information we receive. It evaluates and interprets these stimuli to help us respond appropriately to our surroundings. Next, we will dive deeper into how these functions shape our actions and decision-making processes, particularly in the context of golf. It's like a command center where incoming data is analyzed and decisions are made based on past experiences stored in our memory. For example, it allows us to recognize a specific game situation that requires a particular type of shot to attempt a solution. Motor function. This is responsible for triggering responses to stimuli. Once the information has been processed and an action has been decided upon, this function activates the muscles and organs necessary to execute it. A clear example is when we perform a golf shot. Now, the brain, the neural center of the nervous system, can be divided into three main areas that reflect different levels of complexity in its functioning. 1. The reptilian brain, comprised of the basal ganglia, brainstem, and cerebellum. This is the most primitive and basic part of the brain. It manages instinctive and simple behaviors, such as survival instincts and balance control. 2. The limbic brain, located above the basal structures. This area is closely tied to our emotions and experiences. It forms connections between what we experience and how we feel, facilitating learning in specific contexts and the development of emotional memory. 3. The rational brain, situated at the top of the brain. This area is the epicenter of advanced cognition. It handles complex functions such as reasoning, planning, and conscious decision-making. This is the part of the brain that enables us to reflect on our actions and anticipate consequences before acting. Integrated functioning. It's important to note that this division is an artificial construct. The nervous system operates as an integrated unit, meaning that these parts work together seamlessly to ensure optimal functioning. In this system, its various parts operate simultaneously and in a coordinated manner, continuously interacting with the environment to adapt appropriately to changing circumstances. Neurodevelopment, a path to understanding. Let's now discuss neurodevelopment, which will gradually help us delve deeper into the subject. We can define neurodevelopment as the process of anatomical growth and functional development of the nervous system. This process begins in the third week of intrauterine life and is completed by the end of adolescence, when adulthood is reached. Neurodevelopment involves a maturation process determined by biology and genetics, with a quantitative increase in brain connections that arise from learning acquired through environmental interactions and personal experiences within a social and cultural context. Thus, it is correct to state that the biological characteristics of the nervous system vary and are distinct at each stage of neurodevelopment. This variation leads to different adaptive behaviors and modulates what we are capable of learning at any given time. Precisely. One goal of the development of the nervous system is to respond flexibly to environmental demands, allowing us to adapt and respond appropriately to those demands. When we talk about neurodevelopment, we are referring to a continuous process of change, which should be viewed as a highly dynamic system. In fact, at each stage of the nervous system's development, both its anatomy and physiology undergo significant changes. If the gestational process occurs without complications, humans are born with a nervous system ready to learn from the environment through experience. This learning requires the creation of numerous new connections to adapt to the demands of their new surroundings. Key stages of neurodevelopment. Around 6 years of age, a gradual process of myelination begins in the frontal structures. Myelination is the formation of the myelin sheath around nerves, enabling better signal conduction. This period is critical for the development of executive functions, which are fundamental for regulating behavior. During adolescence, changes in brain anatomy lead to better circuit integration. This is reflected in a reduction in gray matter volume, an increase in white matter, and the reorganization of pathways responsible for dopamine secretion. These changes result in increasingly analytical behavior and more reasoned decision making. It is especially during this stage of development that we must guide our players to reason as effectively as possible. This is best achieved through the formulation of challenges that require complex reasoning. Considering these changes, it is possible to establish phases or stages that facilitate the study of neurodevelopment. These stages are defined by the competencies already acquired, which continue to be refined through new experiences requiring the use of these skills. This perspective helps us better understand the continuous and prolonged process of neurodevelopment, during which the nervous system matures in a sequential manner. However, there is a risk of overlooking the importance of the environment and focusing solely on the biological and genetic components of neurodevelopment, reducing it to a mere maturation process. The environment and the learning experiences it fosters, enabled by and within it, form a fundamental foundation for neurodevelopment. They constitute the psychosocial component that complements these biological and genetic aspects. For this reason, a golf instructor must be capable of exerting broad control over the configuration of the learning environment to design appropriate challenges. The role of neuroplasticity and critical periods. Neuroplasticity refers to the nervous system's ability to modify its activity in response to internal and external stimuli. This process triggers both structural and functional reorganization, and it is in continuous development. However, neuroplasticity is not constant over time. It is greater during periods when neural connections are being formed to accommodate a new function. These stages of neurodevelopment are referred to as critical periods. Critical periods are time windows during which environmental influences have a significant effect on learning a particular function. After these periods, it becomes more challenging to modify different neural networks to develop the same function. Understanding and leveraging these critical periods is essential for maximizing the impact of training and creating an optimal learning environment for players. In other words, identifying critical periods of learning is essential. The key lies in this. When, in line with the previously mentioned ecological theories, the environment provides the appropriate stimulus, it promotes the formation of connections that facilitate learning. If this action is sustained, the student will eventually consolidate the learning. On the other hand, this does not mean that already stabilized structures cannot be modified. However, their plasticity will be reduced, requiring greater effort to achieve effective learning. If we turn to the main focus of this course, executive functions and cognitive abilities, we must first acknowledge that within a psychosocial model, the development of cognitive functions cannot be understood in isolation from the environment in which the individual develops or from the biological substrate that supports them. Temporal development of executive functions. Regarding their temporal development or development period, speaking of a specific stage of executive function development might mistakenly suggest that these functions do not exist or are not expressed before a particular stage. This is not the case, as we have already seen. However, around 6 years of age, as previously mentioned, a period of myelination and functional development begins in the frontal lobe, particularly in the prefrontal cortex. This coincides with an increase in the child's autonomy and greater complexity in environmental demands. This stage is crucial for the emergence and strengthening of executive functions, which are instrumental in navigating these new challenges effectively. Indeed, the development of executive functions marks the beginning of behavioral autonomy and the ability to organize oneself to respond flexibly to environmental demands. Following this, up to around 12 years of age, there are nonlinear periods of intense myelination in the frontal structures, accompanied by further increases in behavioral autonomy. However, it is important to note that the myelination of these structures continues until the early years of the second decade of life. Let's now continue discussing executive functions and cognitive abilities, briefly exploring their history, conceptualization, and the main stages of their development throughout a player's life. Initially, let us examine a definition from the perspective of the information required for decision making and the control of its execution. From this point of view, it is crucial to recognize that we are constantly receiving vast amounts of information processed by our central nervous system, both from the external environment and our internal world. Given the magnitude of possible human responses, brain control processes are required to manage these multiple options. To address this diversity of possibilities, we rely on mechanisms that coordinate both sensory and motor processes. These mechanisms or abilities are known as executive functions. Executive functions reside in the central nervous system, specifically in the frontal lobes of the brain. The structures of the peripheral nervous system facilitate communication between the CNS and the rest of the body. This communication network transmits nerve impulses from the CNS to the muscles and other cells, conveys information from the external environment or the internal milieu back to the CNS. When executive control is underdeveloped or impaired, a person's functional capacity is often severely compromised. This limits behavior to a set of actions that may even be considered dysfunctional or disorganized. This condition is known as the DICE executive syndrome, which encompasses a range of symptoms indicative of dysfunction in the executive control of actions. It is typically caused by damage to the frontal lobes of the brain. Understanding the role and development of executive functions is essential for identifying areas of improvement and implementing targeted strategies, particularly in the context of sports like golf, where decision making and motor control are critical. Although affected individuals may perform routine tasks, they face difficulties when confronted with new activities or situations. Key characteristics of DICE executive functioning: distraction. This is manifested by an automatic orientation towards salient events, regardless of their relevance to the ongoing task, or by succumbing to irrelevant environmental stimuli or tangential internal associations. For example, a player becoming distracted during training, preventing them from learning what is being practiced, perseverance in errors. This refers to the tendency to repeat automatic or overlearned responses even when they are unhelpful in a particular situation. For instance, insisting on using a favorite ball flight when a different, more adaptive trajectory is required for the specific game situation. Lack of cognitive flexibility. This is characterized by the inability to anticipate and modify stimulus response associations according to the external context, or by maintaining rigid stimulus response links that seek immediate gratification. For example, a player focusing their practice on skills they already excel at to experience the immediate reward of hitting good shots instead of dedicating time to learning what they truly need to improve. When do executive functions become absolutely essential? Executive functions are typically crucial in situations that require planning or decision making, error correction or problem solving, contexts where responses are not fully learned or involve new action sequences, circumstances that are dangerous or technically complicated, scenarios that demand overcoming strong habitual responses. These are the moments where well developed executive functions make a significant difference in performance and adaptation. Before diving deeper, let's take a brief look at the history of executive functions, focusing on their discovery, definition, and classification. The first notions of executive functions were introduced by Harlow in the 19th century, particularly in relation to the case of Phineas Gage, a railroad worker who suffered injuries to his frontal lobe after an accident in which an iron rod pierced his skull. This marked the beginning of the study of executive functions, initially rooted in models of brain injuries, which examined the changes observed in individuals who had sustained damage to specific brain areas. Key developments in research, 1923. Feuchtwanger's observations. Frontal lobe injuries were associated with changes in personality, motivation, and the regulation of affectivity. Post WW2, Luria's contributions. Following the Second World War and the resulting increase in cases, Luria linked frontal lobe injuries to programming motor behavior, inhibiting automatic responses, abstract thinking and problem solving, verbal regulation and behavioral adaptation based on the outcomes of actions, personality and self awareness. He later described the functional units of the brain located in the prefrontal cortex, responsible for the programming, control, and verification of activity. 1982. Lizak's definition. Lizak coined the term executive functions, defining them as the mental capacities essential for planning and effectively executing a plan in an independent, creative, and socially acceptable manner. Components of executive functions. Lizak emphasized that executive functions encompass initiating, sustaining, and inhibiting behavior, organizing and generating ideas, self awareness, and the ability to regulate one's actions. These foundational studies have shaped our understanding of executive functions as a critical aspect of cognitive and behavioral regulation. Later, in the 1990s, Goldstein added alterations in functions such as abstraction and mental flexibility to the pathology of the frontal lobe. Since then, numerous definitions of executive functions have been proposed, leading to some conceptual confusion. Today, models continue to emerge that expand or reduce the number of components of executive functions, such as the model proposed by Quine and collaborators in 2010. In this model, executive control is conceived as the integration of cognitive processes that facilitate goal-directed volitional behavior. Here, volitional behavior refers to the ability to decide and regulate one's own actions, closely linked to willpower, the mental process by which an individual decides and determines to perform a specific action. Executive functions in challenging contexts. Executive functions are especially critical in situations where behavior is challenged by environmental or mental distractions and by pre-learned automatic responses, such as automated golf swings performed without the player's understanding and therefore with little to no capacity to adapt to the demands of the game. Key components: goal maintenance and monitoring. This model identifies two particularly relevant components when distractions are present: goal maintenance, a proactive mechanism activated before control is needed and persisting until the task is completed. Monitoring, a reactive mechanism triggered when a conflict is detected during task execution that may compromise achieving the desired goal. For example, when a player realizes they haven't followed the correct process for making a decision, when they notice they have skipped their pre-shot routine. Understanding these components provides valuable insight into how players can develop stronger executive control, improving their ability to adapt and perform under challenging conditions. From here on, a list of definitions for each of these executive functions and cognitive abilities will be presented. The goal is to provide clarity and facilitate systematic study while maintaining the association between them, thus avoiding excessive simplifications and reductionist pitfalls. This ties back to what we previously discussed. From the perspective of dynamic systems, it is impractical to break systems down into isolated relationships, as all elements are interconnected and mutually dependent. Understanding the system is not achieved through a reductionist analysis of its individual parts, but rather through understanding the multiple relationships that exist between them, relationships that are rarely linear. Complex interactions in dynamic systems. In a dynamic system, a single cause will not always produce the same effect. The result will depend on the system's current state and the interactions between its elements at that specific moment. Stages of development, maintenance, and decline. Let's now examine the stages involved in the development, maintenance, and decline of executive functions and cognitive abilities. As observed when discussing neurodevelopment, the cognitive processes that constitute executive functions follow distinct developmental paths marked by key periods in the maturation of their neurobiological foundations. These key periods occur from birth to 2 years of age, between 7 and 9 years of age, during late adolescence, between 16 and 19 years of age. Earlier, it was believed that executive control improved steadily with age. However, growing evidence suggests a nonlinear development. For example, the ability to learn from mistakes and develop alternative strategies emerges gradually during childhood. Young children tend to rely on simple strategies that are often ineffective, random, or fragmented. This highlights the importance of tailoring training approaches to align with the developmental stage of the individual, fostering gradual but meaningful growth in executive functioning and cognitive abilities. Between the ages of 7 and 10, the ability to plan actions and develop strategies to carry them out becomes more organized and efficient. However, between the ages of 11 and 13, a regression toward more fragmented and less elaborate strategies can be observed. This paradox may be related to a conflict between cognitive processes during a transition in the development of executive functions. The implementation of conceptual and holistic strategies can conflict with self-regulation processes, which require breaking down activities to monitor their execution precisely. Balancing and prioritizing these two processes requires executive control, which is only possible when each process reaches an optimal level of development. During adolescence, a surprising contradiction often emerges. Young people know what they should do, but cannot find a consistent way to do it. This leads us to believe, for example, that many talented players do not falter due to technical deficiencies or a lack of knowledge. Instead, they struggle with disruptions in decision-making and monitoring processes during execution. This suggests that, despite common assumptions that adolescents behave similarly to adults, their executive control is still not fully developed. Executive functions typically reach their peak performance between the ages of 20 and 35, following an inverted U-shaped model. Understanding this nonlinear development is essential for guiding young athletes effectively, focusing not only on technical skills but also on fostering robust executive control processes. On the next lesson, we will delve deeper into the definition of executive functions and cognitive abilities. We will introduce an initial classification to help understand the main groupings or categories and explore how to evaluate these functions effectively. For more information, please visit www.cognitivegrowth.pro. See you in the next lesson.